We have 2 more lectures left on statistics, and then of course next Monday is our Unit 5 test. Yes, last class on Monday, we went over measures of center and spread. And for center, we had the mean, median, mode, and the mid-range. And we talked about how all of them, if the data is well distributed, what we call normally distributed, they should be the same number. We did discuss how that with numerical data, the 2 best measures are usually mean and median, and that the mode is really the most useful only for categorical data. You can't do any calculations with it because there's no numbers in the data, it's all categories. But you can tell which one occurs the most often. The mid-range is just kind of a quick estimate. If you know it's a good distribution, you can quickly estimate really the mean and median. Talked about the stability with the mean and median, how the median is more stable or more resistant to outliers, how that one really large number or one really small number can have a huge effect on the mean, but not as big of an effect on the median. For our measures of spread, we had only 2 of them that we talked about in extensively. We had range, and actually there's a third one I'm going to throw in with the standard deviation. We also discussed the variance, which is really part of the calculation. It's a midway in the process of calculating the standard deviation. And how the range, again, was a quick and easy estimate, but it wasn't very discerning. It wasn't very precise, discriminating between 2 sets that were similar. So that standard deviation was a much better measure of spread. Make sure for your test that you have that process for standard deviation down so you're able to do it, because you will be asked to calculate a standard deviation. I wouldn't use a set of more than maybe 8 numbers, maybe 10 numbers at the most, because there's a lot of steps there. So it won't be a huge set of numbers. And of course, mean, median, and mode are things that you're going to have to calculate as well. So now the mean, median, mode, the center, and the spread, we're describing that bell curve. And we talked about how if that data was perfectly normally distributed, of course, the mode is the highest point. The mode, the mean, and the median would all be the exact same number right in the middle of that curve. But if that distribution were skewed at all, so this is a perfect distribution, symmetrical. If it were skewed, for example, we're skewed to the left, that means it's stretched out on the left side, something like that. Well, the mode is still the highest point. The median moves a little bit, gets pulled out a little bit in the direction of skew, but it's that mean that can really get stretched out. And that's one of the ways we discussed for measuring skew, was if the mean was smaller than the median, there's a good chance it's skewed to the left. And then the opposite is true. If it's stretched out in the right side, like this, that is skewed right. And the mode, of course, is still the highest point. The median gets moved a little bit to the right. And it's that mean that can really get, depending on how stretched out it is, that really gets pulled over. So if the mean is bigger than the median, that's a good indication that the data might be skewed right. Well, if we bring in now those measures of spread along with the mean, median, and mode, it can tell us even more about the shape of that curve. So we're going back to assuming that this is approximately really close to being normally distributed, so being close to being that bell curve. The center of that curve could be measured with either the mean, median, or mode. We're going to give the center of that curve, we're going to call it the mean for right now. Again, the mean, median, and mode should all be the same number. And to discuss the spread, what we're going to do is we're going to go out in steps of a standard deviation. So if I go to the right side here, I'm going above the mean. I'm going to add 1 standard deviation. So SD stands for standard deviation there. I've gone up a step of 1 standard deviation. Another step would be 2 standard deviations. So I'd add the standard deviation a second time to the mean. And then another step would be plus 3 standard deviations. And I'm going to come back and put some numbers in there in just a second to make that a little more understandable. Going the other way, I could subtract the standard deviation or step down a standard deviation. So minus 1 standard deviations would be 1 standard deviation less than the mean. Second step would be minus 2 standard deviations. And a third step, minus 3 standard deviations. Well, what does that all mean? Well, a normal curve, these spaces, these ranges have percents that are always there. Now, depending on which textbook you look at, the percents are rounded off differently. I actually usually round them off to the whole percent just to make it easier. But the textbook we use here actually has this curve on page 355. And the way the textbook breaks it down is by just going plus to minus. So 1 standard deviation below the mean to 1 standard deviation above the mean, 68% of the data in a data set should be within 1 standard deviation of the mean if it's an approximately normally distributed set of data. So from 2 standard deviations below to 2 standard deviations above, and actually your textbook, I'm going to clarify this, your textbook instead of using 68%, actually uses 68.3, so I'm going to use their number. Is the minus 1 to plus 1. The 2 standard deviations below to 2 standard deviations above, I usually use 95 in the statistics classes I teach. This textbook uses 95.5, so we'll go with that. It's actually 95.4459, something like that. So 95.5. And then the next range, of course, 3 standard deviations below, 3 standard deviations above is 99.7%. So almost all data in a set will be within 3 standard deviations of the mean. So what does this tell us? Well, let's say we're looking at grades in a course. In fact, let's look at grades for the next exam, for exam 5. And let's say over the last 13 years of me teaching this course, that there's been a mean grade on this test of 89 points. And a standard deviation of 4. So what that's telling us is the center, the mean here is going to be 89. The standard deviation of 4 tells us every step we go, we're going to be adding or subtracting 4. We're adding or subtracting a standard deviation. So plus 1 standard deviation means we're adding the standard deviation. So 89 plus 4 is 93. Plus 2 means we're adding the standard deviation again. 93 plus 4 is 97. Plus that standard deviation again, 97 plus 4 is 101. Going the other direction, we subtract the standard deviation. So we start with that mean of 89 again, subtract 4 gives us 85, subtract 4 again gives us 81, subtract 4 again gives us 77. So what this is telling us now, if I want to know what percent of students score, now let's go score between, let's start with 81 and 97. Well, if I look at that, here's 81, here's 97. So between them is this range here, that 2 standard deviations. That's that 95%, 95.5% range. So we expect 95.5% of students to score somewhere between 81 and 97 on this test. How about between 85 and 93? Well, 85 is right here, 93 is right there, so between would be this range. That's the -1 to +1 standard deviation. That's the 68.3%. If we went from 77 up to 101, well, here's 77, here's 101. That's this full 3 standard deviation range. That's 99.7%. So we would expect nearly all of our students to fall in between 77 and 101. 99.7% means 997 out of 1,000. So no more than 3 out of 1,000 should score outside that range. Well, that's great if we want to go to those ranges, but if we had different questions, let's say we wanted to ask what percent would score more than or above 93. Well, that's a little trickier. Here's 93. Above would be going this way, to the right side of that. Well, how would I get that percent? Well, I'm going to break down these percents for you a little bit. This 68.3%, since this is symmetrical, I can split that up and I can put 34.15% here, 34.15% there. I just split that 68.3 into 2 separate pieces. So what that's saying is if I know that this curve is symmetrical, from the center out is 50%. From here out would be 50 minus that 34.15. That difference is 15.85%. So we would expect only 15.85%, or just less than 16% of students to score more than 93 on that test. I would actually keep going with these percents here, the 34.15 and 34.15. I can do the same with 95. I know that if I divide that 95 in half, from here to here, half of 95.5 would be 47.75. Well, rather than going from the center all the way out, I just want to do this little section here. 47.75 minus 34.15 is going to give us 13.6%. So this little section over here is also 13.6%. Going out from there, the 99.7 from the center out would be half of that 99.7. Half of 99.7 is going to be 49.85. I subtract the 34.15 and the 13.6. What is that? 47.75. So that's going to be 2.10% there. Then, of course, all the way out here is going to be 0.15%, the rest of it. So going in this direction, those percents fill in. Now, these are just the same percents I have up here. I've just broken them down differently. These percents never change. Those for every bell curve, those percents are the same. These percents up here would also be the same. They're just a different way of arranging the ranges. What changes are the numbers down here. They depend on the mean and standard deviation for the set we're working with. Let's take a look at another example of this. So I'm going to start out just by drawing a bell curve and putting those percents in it. So this is 34.15, 13.6, 13.6, 2.1, 2.1, and 0.15. Let's say that you are offered a job and you are offered $16.10 per hour. And you want to know if that's a good job offer. So you do your research and you find that in the area that that job offer is from that geographic area, the mean hourly wage is $15.20 per hour with a standard deviation of 90 cents per hour. So these numbers right here, the mean and standard deviation, tell us what's going to go down here. The center is always going to be the mean. So that $15.20 is the center of our bell curve. Every step we move away from that mean is a standard deviation. So let's go to the right first. Moving up here, every step is plus 90 cents because that's your standard deviation. So 1520 plus 90 cents is 1610. Plus another 90 cents is $17. Plus another 90 cents is $17.90. Going the other way, we're going to go 3 steps down. So 1520 minus 90 cents is 1430. Minus another 90 cents, 1340. And minus another 90 cents is 1250. So let's evaluate our offer of $16.10. $16.10 actually falls right there. Let's say we want to know what are the chances we could find a better wage than that. So better would be larger, so that's these numbers right here. If I add up those percents, I have 13.6, 2.1, and 0.15. I get 15.85%. What that is telling me is that only 15.85% of jobs in that area pay more than $16.10 an hour. So that's telling me that's probably a pretty good job offer. If I wanted to break this down, if I wanted to ask, well, what percent of jobs would I expect to pay between, let's start off with $14.30 to $17 per hour. Well, here's 14.30, here's 17. So between them would be those numbers. I add up those percents. I've got 34.15, 34.15, and 13.60 adds up to 81.9%. So we'd expect 81.9% or almost 82% of the jobs in that area to pay between those two numbers. Or we might ask, what percent would we expect to pay less than $13.40 per hour? Well, $13.40 is right here. Less than, smaller would be the left. Adding up those percentages, we got the 2.1% and the 0.15%. That adds up to just 2.25%. So only 2.25% of the jobs in that area pay less than $13.40. So you can see this as being a useful tool for evaluating something compared to standards in that area. Another example I want to use is for buying a house. Let's say once that you are out of school and working and established, you want to buy a house. And you decide that what you want to buy for a house is a 3-bedroom, 2-bathroom house. You do your research and you discover that in the area that you're purchasing, you've looked at all the selling prices of houses in the last couple of years, and all of the 3-bedroom, 2-bathroom houses that have sold in the last couple of years. The mean selling price is $142,000 with a standard deviation of, let's go $21,000. So what does that mean? Well, we're going to draw a bell curve. And we're going to start out with the center, and we're going to go 3 steps in each direction. These percents are still going to be the same. These percents never change. Like I said, some textbooks might be a little bit different because of different rounding, but they are still the same percent. What goes in the middle here is our mean of 142,000. I'm just going to write 142 to save a little space. As we move up each step, the difference, each step is the standard deviation, which will be 21,000. So going to the right here, plus 21 is 163,000, plus another 21 is 184,000, plus another 21 is 205,000. Going the other way, we subtract the 21,000 each time. So 142 minus 21 is 121,000. Minus another 21,000 is 100,000. And minus another 21,000 is 79,000. Oops, I don't need those extra zeros. So now let's say that you find a house that the asking price is $184,000. And your realtor is telling you, you better put in an offer on this house right now. It's going to sell really quick. It's not going to be around long. We just lost Medford there. Let me finish this example, then I'm going to see what's going on there. So it's not going to be around long. Well, you look here, here's $184,000. If you look at the prices that are above $184,000, that's the right here. Add those percents, that's 2.25%. What that's telling you is of all the 3-bedroom, 2-bathroom houses in that area that have sold in the last few years, only 2.25% sold for more than that. Now, the other way of looking at it is going the other way. Less than, if we add these percents together, that'd be 97.75%. In other words, 97.75% of 3-bedroom, 2-bathroom houses have sold for less than that. So what that's telling me is one of two things. Either that homeowner, that seller, will probably take less for their house, or if they won't, there's a pretty good chance that if 97.75% of the homes should be cheaper than that, there's a pretty good chance you'll find one that's cheaper that you still like. Okay, so the next thing I want to cover, last thing we're going to cover today, this works great if we're comparing one value to a known standard, if we have the information of the mean and standard deviation of the population. But what if we have two values that we want to compare to each other? Going to college, there's a good chance you're going to take placement tests. Let's say you take a math test and an English test. And on the math test, Let's say you have a score of 56. Now, in the English test, you have a score of 71. Now, you're tempted to say, hey, I did better on the English test, but that might not be true. Those tests, the math test might have been way more difficult. They may not have been evaluated on the same scale. To compare them, you can't really compare them to each other. You have to compare them back to their own population to see which one is better compared to its own population. To do that, we use something called a z-score. And a z-score takes a number minus the mean for that population, and then divided by the standard deviation of that population. So let's say that for all the people that have taken that math test, the mean score is 49, and the standard deviation is 4. Let's say that for all people that have taken the English test, the mean score is, oh, let's do 63. And the standard deviation is 5. Well, you look at it, you scored 7 points above the mean for the math test, 8 points above the mean for the English. So it still kind of looks like the English score is better. But let's use the z-score. The z-score here for the math test is going to be the score, 56, minus the mean of 49, and divided by that standard deviation of 4. So 56 minus 49 is 7. 7 divided by 4 is 1.75. Now there's two pieces of information in the z-score. First of all, it's positive. Because it's positive, that's telling us that this value, this number was greater, is larger than the mean, above the mean. 1.75 means that that score is actually 1.75 or 1 3/4 standard deviations better than the mean. You're looking at that bell curve. There's the mean, 1 standard deviation, 2 standard deviations. That value falls somewhere in here. Let's look at the English. That z-score is going to be the value of 71 minus the mean of 63 and divided by the standard deviation of 5. So we have 71 minus 63 is 8. Divided by the standard deviation of 5 is 1.6. So again, that's positive, which means it's above the mean. So on our bell curve, here's the mean. We're above the mean. 1.6 means it's 1.6 standard deviations above the mean. So again, if that's 1 above and 2 above, it's somewhere in here, which means this one is more standard deviations above the mean than the English is. So technically the math test is a slightly more impressive score. Well, where might this be used? Let's say we're evaluating employees. Let's say you're a manager at a retail store and you want to fire one of your salespeople, and you've narrowed it down to 2 people you're going to fire. Let's go with Bob and Steve. And you've decided that next week, whoever has the worst sales is the one you're going to let go. So let's say the next week, Bob has sales of $2,700. Steve has sales of $4,100. Does that mean that Bob is out the door? Well, not necessarily. Let's say Bob works in toys and Steve in electronics. For the most part, electronics tend to be more expensive than toys. So it would be expected for a salesperson in that department to have a higher dollar sales. So what we need to do is compare each of them back to their population. So for toys, let's say that all of the salespeople that worked in toys for that week had mean sales for the week of $3,700 with a standard deviation of $400. And let's say for electronics, all of the salespeople in electronics that week had mean sales of $5,400 with a standard deviation of, oh, let's do $600. So let's look at their z-scores. Bob over here has a z-score. So Bob's sales were 2,700, and we'll subtract the mean of 3,700 divided by the standard deviation of 400. 2,700 minus 3,700 is a negative 1,000. Divided by that standard deviation of 400 is a negative 2.5. So again, there's two pieces of information. The negative is telling us that this is less than the mean, which makes sense. Their sales are below average. 2.5 is saying it's 2.5 or 2.5 standard deviations less than the mean. So on that bell curve, here's the mean. There's 1, 2, 3 standard deviations. Their sales are somewhere in here. Let's look at Steve. Steve's z-score. Steve's z-score is going to be Steve's sales, 4,100, minus the mean for electronics of 5,400, divided by that standard deviation of 600. So 4,100 minus 5,400 is a negative 1,300, divided by the 600 standard deviation is a negative 2.17. So again, it's negative, meaning it's below the mean, but it's only 2.17 standard deviations below it. That means it's somewhere in here. So even though both of them are bad, Bob's is worse. So Bob would be out the door. Okay, so since we only have a few of you in here, we'll cut her off a little bit early today. Homework. The first one is going to be page 357 through 358. I'd like you to do all 1 through 6 there. That's going to be on that empirical rule, which is the bell curve in those percents. And then page 359, 1 through 11, you can just do the odd there if you'd like, and that is the z-scores. These are used a lot in medical practice. If you look at studies for medications or new medical procedures, you'll see a lot of studies published, and you'll see means and standard deviations or z-scores saying, this has a z-score of positive 2.8, which makes it a significant result or whatever. So these are a big deal. Unfortunately, with only 1 more hour of lecture, we're not going to have a lot of time to get into the details of exactly how you'd use those for evaluating data, but it's kind of the basics. So with that, I'll let you guys out a few minutes early today. Friday is going to be our final lecture. We're going to talk about percentiles, measures of position, and then group data. And next Monday is going to be our Unit 4 test. So you guys have a great day, and we'll see you on Friday.